So it's a very common request that we get. Hey, can you make OpenAttestation work in offline mode? Right, and that's the topic of my talk today. So far, our answer for this has been no. It's not possible, like all along, for various reasons. One of it is that you can't get DNS records when you're in offline mode, right? So why do we need the DNS records? We need DNS records to prove identity, right? Because we want to say that a cert was issued with authority from a certain domain. So, for example, like if you've been working on Notarized, you notice that our certs say issued by moh.gov.sg, right? If you've been working on open certs, for the schools, I think we're still like showing just the school names because that's a legacy version. But for other issuers, it actually shows the URL of the domain that issued it. Right, actually, it just shows the domain, not the URL. Right, so for trade trust, I haven't looked at our examples lately, but I think they say example.tradetrust.io or something like that. Right, so that's one of the key reasons that was preventing us from doing offline mode, because I mean, some people say that why don't you just keep a list of valid issuers in your verifier, then you don't need the DNS results. But then when you do that, then why do you even need OA, right? You already know the document can be trusted. All right, so I've been thinking about this for a while, but I never got around to like figuring out a proof of concept. So what I'm going to talk about today is how we can use DNSSEC proofs to verify open attestation identity proofs in offline mode. All right, so let me share this document in case you want to have a look at it on your own screen. All right, so some introduction, right? What is DNSSEC? Right, DNSSEC is a cryptographic extension to DNS. So DNS without DNSSEC is actually what's it's a common mode these days, right? DNSSEC is not very popular yet. The adoption rate is not great. I think AWS actually only added support for it very recently. And so DNS records, are not cryptographically secured, which means that it's actually very, very insecure. Like your ISP, your internet service provider, right, can actually return you results that are completely fake. Right? It can send you to their own domain, and well, you wouldn't be able to know. Right? So DNSSEC was actually specified actually quite long ago already. Like the first specification was, I think, in 2011 or something like that. It was a while ago, but adoption is still not great. Same as IPv6, invented a long time ago, but adoption not great. I don't know. It's just there's a lot of inertia when it comes to like changing the world, right? So the way DNS works is that every every in short, every DNS record has to be signed by some key, and this key has to somehow have a unbroken trust chain, right, all the way up to the root anchor. And the root anchor is just a key that is published. We call it a well-known, right, which means that like a trusted individual has like said that this key is the key that is the root key, right. Beyond that, you can't really get any further than that lah, in terms of like a trust, right? Right, because like how do you say like what is the canonical root key otherwise, right? So there's the one key that everyone recognizes, and it's actually stored in a physical vault, right? And I think you need more than a few people to open it. Okay, so how do we get like from, let's say we have a TXT record on moh.gov.sg, how do we get from that to the root key, right? So I found this DNSSEC visualization website. All right, I took a static screenshot. Let me see if this works. All right. Okay, so this is all pre-filled already. I pre-filled it with moh.gov.sg, right? And it's looking for TXT records only. Right? So DNS records come in various flavors. So like A, TXT, MX, all the different records. But the one that I'm interested in is TXT records. All right, so we start from here. Right, this is the bottom, and this is the top. Right, the top is the root keys. Okay, so we look at the bottom. Right, so this is the set. I think it's a bit small for you to see. Can I make this bigger? Yeah, I can make this bigger. Right, so you can see that the record data here, this is all the TXT records that exist on moh.gov.sg. Right, you can see we have two records there that are DNS-DID. So these are our own records. The rest are various other records. For example, the V equal SPF, that's for like mail, right? Then there's a bunch of AWS, SES stuff, etc. Right? So this is the set of all TXT records that exist on moh.gov.sg, and then over this whole set of TXT records, it's signed, right? It's signed. This thing doesn't show you what the signature looks like. So, but this whole set of records is signed, and then it's signed with this key. Right, you can see it says L equal 8, ID equal 40569, right? So that's the key that this set of records is signed with. So there are various algorithms. I believe 8 is RSA. I don't remember the exact numbers. 8 is RSA and 13 is ECDSA, I think. Right, and then there's one more that I haven't looked into it. Right, so this is the key that is used to sign this, right? And then it's verified against this key. And then this key verifies that this record for the key is signed, right? So it's like a whole bunch of like interaction, right? And then so this key is actually signed by itself, right? This key is signed by itself. So what does that actually tell you? It doesn't tell you anything, right? But like if you just take this on its own, it has not received any external validation that this is actually valid, right? So what we do is we go up one level, right? We look at up one level. I think this is .gov.sg, right? So .gov.sg, right? It has a DS record, right? This DS record means is a delegation record, right? Delegated signature. I don't remember what the S stands for, right? Which just says that hey, I am a record on .gov.sg, and I recognize that moh.gov.sg, which is below me, uses this key, right? So this record attests for this one below. Okay, then we look at this and we look at the signature on this DS, right? And then we go up and then we check the signature again, right? And then we go up again, right? So this one is for SG, right? So .gov, then you have .sg is above .gov, right? So .sg has its own key, and we do that whole thing again. We check everything, right? And then from here, then we go up one level, right? So this is the DNS key for, if you can see, it's very small. It says DNS key for just dot, right? So dot means it's the top level already. Like there's nothing else above it, right? So that is the root key already. Okay. So that's how it works. So basically, when you verify this, you have to resolve everything all the way until you reach this key that you recognize. And everything in between has to check out. They're all like signed with like private keys that are not on the internet, but then there's the public key that is published here. Okay, so that's the long and short of DNSSEC. It's actually not too different from like how OpenAttestation like Merkle roots work. It's somewhat similar, right? Not exactly, but somewhat similar. Right, so the recursive, right? So here we talk about the root key that I already mentioned earlier. So the root keys, you should not assume that they are static, right? They change every now and then. Right? The first key was deployed in 2010, and then there was a replacement that was deployed in 2018. You're gonna ask why they deployed a new key, right? It's not because they like lost the key or anything, and they just decided to do it because it's regular security practice. You should be rotating your keys every now and then. Okay, and then it looks like the process is that they'll deploy the new key, and then 4 months later they will revoke the old one. Okay, and there's an automated procedure for that. So this means that, you know, the offline verifier, right, needs to keep up to date whenever there's a new root key lah, and also needs to keep a history of all the previous root key. If not, they can't validate like previously issued documents. Right. Now let's talk about how this works inside a how this could look like inside an open attestation file. Let's open this image. So this existing online verification flow, if you're not familiar with it, right? The open attestation document looks like this. All right, we have a template. It has an embedded renderer and it has URL, and then it has an issuer with a identity proof. So in this case, I used the DNS DID type of record, right? It has a location. Right? So when we verify this, the simplified version is that we look up this DNS record. We look for all the records on example.com, and then we find if there's any open attestation records here that matches the signer on this document, right? So if there's a signature that matches, we do the signature verification, and this means that if the signature verification checks out, it means that this private key for the public key is like that was used to sign on this document, right? Sign the hash of this document. Okay. So then at that point, we know that it was a valid cert that was issued, right? But that's not the only thing that we need internet access for. We also need to load what it looks like, the renderer, the template, right? So that's what this part of the document is, right? We actually load this URL, right? We load it in the iframe in this part of the website. If you look at our website, they all have the same format. You have this header above, and then we have this iframe below, right? So this iframe contains the code that was published at this website, hosted at this website, and then what we do is we just pass the OA document into this renderer, and then we let the renderer do its thing. We don't actually interfere with it at all. Okay, so this is the existing verification flow. Now, how can we do this for offline verification? Right, so the fact is that for offline verification, you will have to issue new documents, right? Because you can't just like update the old documents to work offline. Okay, so there's a issuance step, right, that looks a bit like this, right? What we'll do first is we will pre-render the OA document into some sort of like a visual representation. For my proof of concept, I'm going to use the SVG format. Right, so I'm just pre-render OA document into SVG. We'll store this visual representation inside the template object. We'll store it as a string for now, right, for proof of concept purposes, right? And then this is the fun part, right? This is the fun part where we have to do the DNS stuff. So I've written a library that fetch the sign proof for records and also verify them. And then we'll put this whole bunch of proofs. I have an example later, you can see. That we'll put that into the identity proof section, right? We'll just put it inside this object here. Then when it comes to time for verification, right, there's this offline, we call it non-interactive process. Right, there is a term in cryptography. Non-interactive means that I don't have to query the signer. I don't have to ask the signer, hey, did you sign it? Right, because I can check it myself. I can do it offline. Right, so the first part is to verify that the DNS records in here are actually correct, and also that it matches like the claimed issuer. Right, so for example, I claim to be moh.gov.sg that issued this document. I have to check that the proof in here actually includes like moh.gov.sg, right? And then after that, we do the same thing. We verify the document integrity with the record in the DNSSEC proof, right? And then for the template, we will just directly render the picture. You don't have to pass documents around or anything. Okay, so that's like simplified. Okay, so that is how it could possibly work. It's still a proof of concept stage. I mean, I haven't even written the proof of concept. I just wrote the library for the DNS records. Right, so there are some like considerations here that I'm not going to go over in detail here. It's not, you can read it if you want. All right, so one key problem, right? Yeah, it's a problem. Like if you're doing offline verification, you cannot receive like real-time information on whether a document is revoked because you can't query anything because you're offline, right? What the best thing you can do is like just like fetch it on a daily basis, store it offline, and then check against these records, right? So that's like one way you could still have a revocation, but we don't have a method that looks like this lah. If we want to do that, we have to update the we have to write a method for that lah, right? So one way to get around this is when you issue an offline capable document, right? The lifetime of the document should be short. Like it should only be as long as like it should not be longer than you need it for. Best case, like maybe like 1 day, right? Or maybe a vaccination cert, you issue it on demand. When the person requests it, you issue it a valid one that lasts for 1 day. And then if he needs another one, make it easy for him to request more, right? So that way the lifetime is short and it expires naturally, right? Instead of relying on revocation. I mean, another potential option that occurred to me the other day is to use Bloom filters, right? So Bloom filters allow you to compress data, not exactly compress data, right? You can store true or false, right? Inside a Bloom filter. When you query a Bloom filter for a document, right? What it tells you is it's actually a probabilistic data structure. I don't think I want to go full into this, but there's a chance of a false false positive, but there's not a chance of false negative, right? So if it's inside, it will definitely be inside. But if it says it's inside, there's a small chance, depending on your parameters, that it may not be inside. But there's like some innovation here with Mozilla's CRL lights that actually fixes that. But that just occurred to me the other day, and I don't know if I want to implement that. All right, so that is a very quick overview of how this could work. I haven't done proof of concept example here. And in the appendix here, you see like what example set of records look like. Right, so you see a TXT record right over here, and then it has a signature so the RR sig, right? The RR sig is a matching signature for the record, and the RR sig is never just for one record. It's for all the records on that domain. Okay, so if I have 3 TXT records, there's still one RR sig on it. Okay, and then all these are like all the way up to the root. Okay. Okay, so that is my talk for today. I'll just say, anyone have questions? No questions?
Yeah, I was curious when you were talking about DNSSEC, right? The root being the just one dot. So what happens if let's say that particular key gets kind of exposed, or will it cause the rest of the other domains to have issues as well?
Okay, so that one is a bit tricky, right? I mean, like I said, there's a process for rotating it, but I'm pretty sure there will be a lot of havoc if like they had to change it on a 1 day notice, right? So fortunately, that's why they store it in a physical vault, right? The private key is actually stored in a physical vault. So I don't know, but I believe it's probably stored in a HSM as well, a hardware security model, which means that you cannot expose the key. Like you cannot exfiltrate the key. You can only like take it out. I think they won't even let you take it off the premise. Like you can bring something in for it to sign, right? Then once you have done your thing, then they're gonna lock up the vault again. So that's how they work around it lah. Because I think I'm pretty sure like if you change it on a 1 day notice, nobody will update that quickly. Right? There's an automated process, but I don't think many DNS servers have like implemented that.
I see. Very interesting and very scary at the same time.
Yeah, it's the keys to the internet. Lauren, you look like you have questions. Like you have a lot of stuff going on in your head.
No question.
Okay. Cool. If there are no more questions, then that's it for me today.
Thank you.